Welcome to Exponential and Logarithmic Equation and Inequalities. For today's objectives, we want to learn how to solve exponential and logarithmic equations and inequalities. In this first example, we're going to be solving two exponential equations. So let's take a look at example A. In example A, we have the exponential equation 8 raised to the x equals 2 raised to the x plus 6. So our first step here is to make both bases equal. So right now the first base is 8 and the second base is 2. Now we want both of these bases to be equal, so it's easier for me to change 8 to 2 than it is to change 2 to 8. So if I make 8 2 to the third and still keep that times x up here, I can say 2 raised to the third times x equals 2 raised to the x plus 6. So now that both of my bases are equal, I want to make both of my exponents equal. So we're going to make exponents equal. So my first exponent is 3 raised 3 times x, and my second exponent is x plus 6. Now I'm going to solve for x here, and I have 2x equals 6. X is going to equal 3. There are two main steps here. First step is to make both bases equal. I did that by changing 8 to 2 raised to the third. And the second step is to make both exponents equal. Now I can check that by plugging in 3 into my original equation. So let me just make a little line here. I want to have some space for this problem over here. So if I plug in 8 raised to the third equals 2 raised to the 3 plus 6. 8 raised to the third is 512. And then I have 3 plus 6 is 9. And 2 raised to the 9 is 512. So my answer of x equals 3 works. Okay, so for the second example, it's a little more difficult to make 5 and 200 be powers of each other. So since we want to do the inverse operation here, we want to take the logarithm of both sides. So whenever we have an exponent equation, if we want to solve for x, we have to do the inverse. And we've learned that the inverse of taking an exponent of both sides is to take the log of both sides. So what we're going to do in our equation is take the log of both sides. So our first step is take the log of both sides. Now we could have done that here on part A, but here is a little easier so we didn't have to do that, but it would have worked for example A too. So we took the log of both sides, but an important part to remember is the base should be the same as the exponent base. So what I mean by that is here we should take log base of 5. Because that will eliminate that 5. And that will be good because then we get the x minus 2. So what we want to do here is we want to do log base 5 of 5 raised to the x minus 2. And we did it on this left side, so we want to do it on this right side too. So we have log base 5 of 200. So we learned in the previous section that if we take the log base of another number that's similar, these things just cancel out. So left side becomes x minus 2 equals log base 5 of 200. So now what we need to do is we need to do the change of base. So we're going to isolate x, so we're going to say x equals 2 plus log of 200 over log of 5. Now this last step that I did here, that is called the change of base formula. You should have already learned that, but if you need to research it, just research change of base formula. So we punch log 200 over log 5 in our calculator, add 2 to it, and our answer, I don't have any more space down here, our answer is about 5.2. So taking the log of both sides work, but if it's an easier one like part A, you could just make both bases equal. But this will work every single time, taking the log of both sides. Okay, let's try some more practice problems to use both of those methods. So for this first method here for part A, what we're going to be able to do is make both bases equal, since 3 is a power of 27. So we have 3 raised to the 2x equals. Now, for this one, I have to make 27 have a base of 3. So I know 3 raised to the 3 gives me 27. Now, both of my bases are equal, so 2x has to equal 3. And x equals 3 over 2. Okay, for part B. Now, I know that 7 times 3 is 21, but there's no way that I can raise 7 to any number that will give me 21. So for this one, I need to take the log of both sides. Now remember, I have to take a log that has the same base as this. So what I do log base 7 of 7 raised to the negative x. And if I do it to one side, I have to do it to the other side. So I do log base 7 of 21. Now when I did this on this side, this gets eliminated. I'm left with negative x equals log base 7 of 21. Now we have to do the change of base formula. So we have negative x equals log of 21 over log of 7. Then I'll have negative x equals 1.56, and I can have my variable be negative, so I have x equals negative 1.56. So once again, this step right here is the change of base. Okay, let's try this last one. For part C, once again, I can't make 2 be a power of 15, so I have to do the log of both sides. So I do log base 2 of 2 raised to the 3x equals log base 2 of 15. Then this becomes 3x equals log base 2 of 15. Then I have 3x equals log of 15 over log of 2. I divide both sides by 3, and I'm left with x equals 1.302. Now we're solving logarithmic equations, and the idea is very similar to exponential equations, except we're going backwards. So, when we had an exponential equation, to solve for x, we had to do the inverse. So to do the inverse, we took the log of both sides. So now when we're solving a log function, we still have to do the inverse, but the inverse is now exponentiating both sides. So this term that we're going to use is called exponentiate. So I'm going to be using that term. I want to make sure we understand it. Let's look at part A. For part A, we're doing log base 3 of x minus 5 equals 2. So I have to exponentiate both sides by a certain number. The question is, what's that number? Well, I have to exponentiate both sides by whatever number this is, because that's going to eliminate this log, which is what I want to do. I want to get x by itself. I have my equation log base 3 of x minus 5 equals 2. So the first step is to exponentiate both sides. So I'm going to exponentiate by 3. So I'm going to have 3 raised to the log base 3 of x minus 5 equals 3 raised to the 2. Notice I exponentiated both sides. I'm taking both sides, and I have this 3 as my base, and I'm bringing these up to be exponents. So when I do that, what's going to happen is this right here is going to go away. And I'm just going to be left with x minus 5 equals 3 squared, which is 9. And x is going to equal 14. For the next problem, we have two log functions that are being subtracted from each other and that are being equal to 1. Now we know from the previous section in our study of properties of logarithms that if we have two logarithms that have the same base and they're being subtracted from each other, that belongs to the quotient property. So the first thing we're going to do here is apply any property that's going to allow us to simplify this. So since these are both common logs and they're being subtracted, we're going to combine them into a fraction. So we have log of 45 times x divided by 3, and that's going to equal 1. Now we know 45 divided by 3 is equal to 15, so we have log of 15x equals 1. So now I want to exponentiate both sides to get rid of the log. So the next step is to exponentiate. I'm going to do that by the number 10. I picked 10 because this is a common log. Technically, remember, there's a number 10 here. So I exponentiate both sides by 10. And when I do that, the log goes away and I'm left with 15x equals 10. Now it's easy to solve for x. X is going to be equal to 10 over 15 or 2 over 3. Now you can always plug these back in for the x values to see if they work. Let's try a few more practice problems. Now for these ones we're going to have to apply some properties before we do them to help solving for x. So for example C, we have log base 4 of x squared equals 7. So similar to the previous one, I want to apply any properties that's going to make this simpler for me. So I have this x squared, so I know I can apply the power property. So I'm going to take this 2 here and bring it to the front. I'm going to have 2 times log base 4 of x equals 7. Now the next thing I want to do is I want to isolate the log. So I'll do that by dividing both sides by 4. So I'm going to have 2 times log base 4 of x equals 7, and I'm going to divide both sides by 2. When I do that, I have log base 4 of x equals 7 over 2. And then now that log is isolated, I want to exponentiate both sides. So I'm going to exponentiate both sides by 4. And then this goes away. I'm left with x equals 128. Let's look at example D. In example D, we have log of x plus log of x plus 9 equals 1. So let's apply a property here to combine these two logs. So I'm going to apply the product property. And I'm going to combine these. So I'm going to have log of x times x plus 9 equals 1. Now you can simplify this part out if you would like, or you can leave it like this. Either way, it's still going to come out to be the same. So now I have my log isolated, so now I want to exponentiate both sides. Now this is a common log, so I'm going to exponentiate both sides by 10. When I do that, the log goes away, and I'm left with x times x plus 9 equals 10. Now here's an equation that I have to solve for. So we have to factor out the left side and solve for x. So we're going to have x squared plus 9x, and we'll subtract 10 to put this in standard form. So now in this step, I have to factor. So I need my two binomials, and in the first spots I need two terms that multiply together to give me x squared, and I need two terms that multiply together to give me negative 10 but combine to give me positive 9. So I know I need a 10 and a 1, and since this is positive, this will be positive, and we need a negative to make this negative. So my x values are negative 10 and x equals 1. Now once you finish these, you have to check them. We have to check our answers. And we do that by taking our x values and plugging them right back into here and here. Now this first one doesn't work. Our first solution for x does not work because you can't take the log of a negative 10. So this answer does not work. So our real answer is x equals 1. Now let's use some of the techniques we've developed to help us solve this logarithm equation. So we have the equation 3 equals log 8 plus 3 times log of x. Now before I apply the product property and multiply these two terms together, I want to take care of this 3. I want to get that out of the way. Now I know that if I have a term outside of a log equation, I can bring it out here using the power property. So the first thing I'm going to use is the power property because I don't want anything in front of those log functions. So I'm going to have 3 equals log of 8 plus log of x raised to the third. So now I have nothing in front of my log equation, so I can combine these using the power property. So we'll use the product property, and we'll have 3 equals log of 8 times x to the third. So I have my log equation isolated, So now I can exponentiate. Now this is a common log, so the base is 10, so I have to exponentiate both sides by 10. So I have 10 raised to the 3 and 10 raised to the log of 8x to the third. So now I simplify, and my equation looks like this. 10 raised to the third equals 8x to the third. So now I have to simplify and solve for x. And now we're just using algebra to figure out what x equals. So I know 10 raised to the third is 1,000. Then I have 8x raised to the 3. I'm going to divide both sides by 8 because I want to get x by itself. So I'm going to have 125 equals x to the third. So now I'm trying to figure out what the cube root of 125 is. So I take the cube root of both sides. So this is how we denote the cube root. Try to figure out what number times itself 3 times gives me 125. And then I have the answer is x equals 5. And that's our final example of solving logarithmic equations and exponential equations. I hope this was helpful, and once again, you can go back and watch any problems in the video that you would like. Alright, thank you, take care.